And God willing, this share screen thing will work. Okay, great. So now we're all set up. So let's just recall at the beginning what the theorem was from last time. So the goal was given a sequence of tuples I, which is AI, I less than omega, find an A indiscernible sequence J such that J somehow closely resembles I. And we gave precise meaning to what closely resembles should mean in terms of something called the EM type. So let's recall that the EM type was just of I over A should be,
Nick,
yeah.
check the chat.
Ah, so someone can't see me. Can others see me? Okay. So if you can't see, then perhaps you should try like leaving and then coming back or restarting your Zoom or some such thing, because it seems like it's working for most people. All right. So the EM type of I over A was just the formulas that are true on all increasing intuples from the sequence. So this is formulas.
Am I supposed to be seeing your face or the screen right now?
I'm sorry?
Am I supposed to be seeing the face or a iPad or something?
The important thing is that you see the iPad.
Oh, no, I see your face and I don't see anything.
Oh, okay. Well, at the top, perhaps you can click the iPad. I'm not sure.
Okay. I don't know why I clicked, but now I'm back to the iPad.
Okay, so everyone can see the iPad, yeah? Okay, very good. All right, so the EM type of I over A was just the formulas phi in LA such that for all increasing intuples I bar from I, we have that phi A I bar is true. So, of course, if you have a sequence which is not indiscernible, then maybe you have things which are true somewhere, but not true elsewhere. So the EM type just encodes the things that are true somehow, no matter where in the sequence you look. So this is somehow like the indiscernible content of the sequence that you were given. So you have some sequence where some of the behavior changes as you move along the sequence, and some of the behavior is constant. And what the EM type does is it picks up on the constant behavior. And so you know that if you have some sequence and it's not indiscernible, then some of it will be constant and some of it will change. And if you want to have an indiscernible sequence that closely resembles the sequence you were given, it of course can't copy the changing behavior because it's going to be indiscernible. What it can do is it can copy the constant behavior. So that's somehow as good as you can do. And that's exactly what the EM type codes. So last time we proved the following theorem.
Nick, I have a question.
Yes.
Suppose the sequence you start with is an indiscernible sequence.
Yes.
And you want to compute its EM type. Then what do you get?
You get the type, actually.
You get the type of the sequence?
Yes, it's exactly the same as the type. So in fact, it's an exercise in definitions to show that a sequence is indiscernible over A if and only if its EM type is complete. And the argument for that is as follows. So if a sequence that you're given is indiscernible, then no matter which increasing intuple you take, the formula will be true or false, regardless of the intuple, right? Because that's what indiscernibility means.
Right.
So that simply means that every formula gets a truth value. Every formula is either in the EM type or it's out of the EM type, so it's complete. Now, suppose you have some sequence such as the EM type is not complete. Then what does that mean? There's going to be some formula that is omitted. And that means that you have to be able to find two increasing intuples where the behavior is different. Or likewise, if you have a formula, if you have a sequence which is not discernible, then there have to be two places where the truth value differs on some formula. That formula won't be in the EM type. That's another way of seeing it. Is that clear? Okay, cool. So right, so this is a nice point. The EM type is complete if and only if the sequence is indiscernible. All right, so here's the theorem. So the theorem is just that you can do it. So given a parameter set A and sequence AI, I less than omega, there is an A indiscernible sequence J, which realizes the EM type of I over A. And this is what we did last time, and the proof last time was by Ramsey's theorem.
So Nick, I have a question about the statement of the theorem, which
Yes.
I didn't think of it last time, but when we say that there exists an A indiscernible sequence J, are we assuming that it lives in some elementary extension of the model we're working on, or that the model is sufficiently saturated?
Yeah, okay, so maybe it's worth actually saying this explicitly. So let's just fix conventions. So T will always be the theory I'm working with, which is complete first order in the language L with monster model M, and everything lives in M. So this is the normal model theoretic convention. You don't really care about studying models of the theory so much as you care about studying the definable sets and the objects that you can build modulo of the theory. So you just sort of fix some, huge model, which is very saturated, very homogeneous, and then everything you ever care about will be considered as living inside of this structure, and all the objects that you think about will be small relative to the size of this model. So I can always assume that everything in question, like maybe I have A down here and some sequence I, then I know because A is small, I can find some J living inside. There are several places where I've done things like this. Like here, I wrote models v A I bar without writing a model. So what do I mean? I mean that it's true in the monster model, that it's somehow true in the biggest model. And there will be, of course, a few places when we need to somehow work with particular models, but for the most part, when we say that there is something, we always mean it's a subset or a substructure or a subtuple of the monster. So I'm glad you pointed that out, because I think if you do model theory for long enough, then you forget that you have to fix this convention, that it's not just a self-evident kind of thing. But yes, that's a good point. So when I say that there exists something, I mean in the monster model, or as you point out, in any sufficiently saturated model. A plus saturated would be enough. Okay, good. So anyway, back to this point. So last time we gave a proof, which was by Ramsey's theorem. So what was the argument? Well, you can write a partial type, which says I'm A indiscernible and I satisfy the EM type. And any finite subset of that partial type will only talk about finitely many formulas. And those finitely many formulas can give you they can give you a way of cooking up a coloring of the sequence that you were given based on which of the formulas in that finite set are true or false on a given increasing intuple. And by Ramsey's theorem, you can find a homogeneous subset. And that is exactly the same thing as something which is indiscernible with respect to that finite set of formulas. But because it's a subsequence of the sequence you started with, it of course still realizes the EM type. And that's exactly what you need to run the compactness argument. By compactness, you know that this whole thing is consistent, and that gives you the sequence you want. So that's one way of arguing this. And now the rest of today, I want to give a completely different proof. And the proof will be important because it introduces some objects which will be really fundamental to what goes on in the future. So let's just fix a definition. So recall that if A is a set of parameters, S x of A is the set of complete types over A with, in the variables x. Okay, so recall that a complete type over A is just a maximal decision about which formulas are true and which formulas are false of the variables x. So it's a maximal consistent set of formulas where the parameters come from A and the free variables come from x. Now, if A is the monster model, we call Sxm the set of global types. So this is just convenient notation. Whenever we have a type which is somehow over everything, then we call it a global type, and that makes sense. So the key definition, sorry, let me leave it there. So the key definition is the following one. So a global type P in Sx of M is called A invariant if the following thing happens. So whenever I take a formula, phi xy, which maybe has parameters coming from A, then if B has the same type as C over A, then phi x B is in P if and only if phi x C is in P. Okay, and then there's an equivalent definition which I'll give, or equivalently, sigma star P is equal to P for every sigma in the automorphism group of the monster model fixing A. So there are a lot of things that need to be explained here. So let me zoom out a bit. So how does the automorphism group act on types? Well, this isn't so confusing. If you just have phi x, let's say B in P, that happens if and only if phi x sigma of B is in sigma of P. So sigma star of P. So sigma acts just by translating the parameters. And that gives you an action of the automorphism group on types. And okay, when I write M over A, that's the automorphisms of the monster model that fix A pointwise. So this latter definition explains why it's called invariant. It says that it's not changed by automorphisms. But the real concrete meaning is that if you have a formula, then the question of whether or not an instance of that formula goes in the type depends only on the type of the parameters over A. Somehow A has all of the information. So let's draw a picture. So let me zoom out some more so that the definition stays up. So here we have the monster model. And then down here I have some small set A. Now, if I take 2 points, B and C, and let's assume that they have the same type over A, then, and the first definition says phi xb goes in the type if and only if phi xc goes in the type. So the decision about whether or not a formula goes in the type depends only on information contained inside of the set A. But for those of you that remember from model theory, in a saturated model, 2 elements have the same type over A if and only if there's an automorphism that takes one to another. So if you have some automorphism fixing A, taking B to C, then the second definition certainly implies that phi xb will go in the type if and only if phi xc goes in the type for the automorphism that takes B to C. And so it's an easy exercise using this fact that 2 things have the same type over A if and only if they're conjugate by an automorphism fixing A, that these 2 definitions are equivalent. Okay. And the way you should think about it is that somehow, even though the type is global, even though the parameter set is the entire monster model, which is some huge thing, somehow this is a type which is very compressed. All of the essential element information about the type is contained in the set A. The decision about how to build the type is somehow encoded in information in A. So you should think about it as, even though you have some very big piece of information, namely the whole type over the whole monster, the essential information is compressed into this small set A. So these types have very special properties. Okay, is that clear? All right, so this is the definition of an invariant type. And now here is a key property of invariant types. So here's a lemma. So suppose P is a global A invariant type. And AI, I less than omega, is a sequence such that AI realizes P restricted to A less than I for all I less than omega. So what does this say exactly? So this symbol is restriction. So if you have a global type, you can of course restrict it to any subset of the monster model. And so what this is saying is I have my type, and I first realize it, and then over my realization, I realize the next one. And then over those 2 realizations, I realize the next one. And over those 3 realizations, I realize the next one by one by one. So suppose I've done that. Then the sequence AI, I less than omega, is A indiscernible. Okay. Now, there's an intuitive reason why this should be true, which is just that all of the essential information about the realizations are contained inside of A. So each time you're just sort of asking, okay, what does A think about this stuff? And A is not getting any new information as you're generating the sequence step by step by step. So you would expect that A can't distinguish between these elements. And we'll see that that's sort of more or less how the proof goes. But let me just draw a picture so that we...
Sorry, Nick, could you repeat what A sub I satisfies P restricted to so-and-so means again? So does it mean the entire sequence satisfies the type, but now you just take parameters from...
Yeah, so let me draw the pictures again. So here we have the monster model, and we have some type which is over the monster model, P, right? So because P is over the monster model, we can realize it over any subset of the monster model. Like if you have a type which is over a big set of parameters, you can also restrict that type to any smaller set of parameters, and you get a subtype, right? So let's first look at the set A, the set over which it is invariant, and then we just look at P restricted to A. So that's some very small type. It's not global at all. It only knows about A. And then we'll realize that with A0. Okay? So A0 is going to be like this point. Then we get a slightly bigger set, namely A together with A0. And then what do? We realize P restricted to A together with our new realization. That's A0. And the realization is called A1. Then we get a slightly bigger set, namely A0, A1. And then we let A2. Okay, the dog's a little upset.
I'm sorry, Nick, are you writing something? I can't see anything being.
Oh no, it's lagging again. That's weird. Okay, let me stop sharing and then start again. Thank you for pointing this out. Okay, yeah, now we're good. Okay, so yeah, so this is what I was writing. So we first look at P restricted to A, and then we realize it. Call the realization A0. Then we look at P restricted to A0, and we call the realization A1. Then we look at P restricted to A0, A1, and we realize it with A2. And then we continue this way.
The A sub I are sequences. Each, like A0 is a sequence.
No. So each one is just an element. It's a tuple. So remember, P was a type in the variables X. So if X is like a singleton, then each AI will be a singleton. It'll be an element. And we're just taking realizations of this given type, and step by step, we generate a sequence, which is the sequence of these AIs.
Okay, thanks.
Okay. Great. Yeah, no, I mean, this is a super important construction that we will do just a billion times. So it's really important to get it clear. All right, so what do we need to prove? So what we will do is we will prove by induction on n less than omega that if I0 is less than ... is less than I n minus 1, and J0 is less than J n minus 1, then what happens? We have that I0 through AI n minus 1 has the same type over A as J0 through J n minus 1. Of course, this is what we need to prove if we want to prove that the sequence is indiscernible. That if we take any two increasing n tuples from our index set, which in this case is omega, that the tuples that they index have the same type. So we generated a sequence in a particular way, and now we want to check that they all have the same type. And we're going to do that by induction on the length. So the case of n equals 1 is easy. Why? Well, because let's assume without loss of generality, for example, that I0 is less than or equal to J0. We can just make a choice about which one is bigger. Then we know that I0 realizes P restricted to, well, actually this bit about, this is not necessary. Forget this for a second. So we know that I0 realizes A less than I0. So in particular, I0 realizes P restricted to A. If I take a type and I realize it over a big set, then I certainly realize its restriction to any smaller set. So if I just restrict to A, then I have a realization like that. Now, J0 realizes P restricted to A less than J0. So J0 realizes P restricted to A too. But P is a complete type over the monster model. So certainly its restriction to A is a complete type over A. So they both realize the same complete type over A. So that implies that AI0 has the same type over A as AJ0. So this is because P restricted to A is a complete type over A. Does that make sense? So in this case, it almost just follows by definition. Okay, so now, sorry, let me leave that. So now let's assume it for N. And consider let's call this I0 less than dot 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 less than I in now, and J0 less than dot 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 less than Jn. Okay, and now we're going to make this without loss of generality assumption that In is less than or equal to Jn. Of course, one of them has to be less on the nth one. So just so we have a picture, here we've got omega, and let's say N is like 2. So we've got 3 things. And so maybe the black ones, let's do it this way. Back. So here we've got omega. And here we've got like the I0. Just like I0, I1, I2. And then we've got, I don't know, J0, J1, and J2, something like this. Now, what we know by induction is if I look at this pair and this pair, they have the same type over A, because that's our inductive hypothesis. So now we want to prove the same thing for the triple. Okay. So let's do that. So again, by the inductive hypothesis, we know that I'm going to write it in abbreviated form. AI less than N has the same type over A as A J less than N. And now it's really just a matter of using our definitions. So then for any formula phi x y in LA, we have that phi AI in of AI less than N is true, if and only if what? Well, how did we take AI less than N? Or sorry, AI in. AI in was a realization of a particular type. Which type? Let me zoom in a bit because we're running out of space. So let me shrink this. Okay, if and only if this thing is an element of P restricted to A less than I sub n, right? Why? Well, because I sub n is just a realization of this type here. So any formula that's true of it has to be in that type because it's a complete type. So this is just by the construction. We chose AIN to realize this type. So anytime that a formula is true of it, it has to be there because it's complete. Now, this happens if and only if phi x AI less than N is an element of P restricted to A less than J sub N. Why? This is just because I sub N is less than or equal to J sub N. So this type here is contained in this type here. So if I have a formula that's here, it has to be here. And vice versa, because the parameters come from the smaller set. Okay. Now, here's where we use something interesting. This happens if and only if phi x I sub less than n is in, sorry, this is j sub less than n, is in p restricted to a less than j sub n. Now, why is that? This is where we use a invariance plus the inductive hypothesis. So what invariance told us is that the question of whether or not a formula goes in the type is determined entirely by the type of the parameters over A. So our inductive hypothesis told us that A I sub less than n, this thing, had the same type as this over A. So because these two underlined tuples have the same type over A, and this type P is A invariant, I know that this goes in the type if and only if this goes in the type. But then we remember how we chose A sub j sub n. It was a realization of this type. So this means that this holds if and only if phi A sub j sub n of A j sub less than n. And since that holds for any formula, in LA, we showed A I0 all the way through A I in has the same type over A as A J0 through A Jn. And that's the theorem. Okay, does that make sense? So this is really just an exercise in unraveling the definition of invariant. You have to organize the induction in the correct way, but what this tells you is that you can sort of inductively realize an invariant type, and doing so, you generate an indiscernible sequence. So now what we're going to do is we're going to produce invariant types. So this lemma says that if we have invariant types, then we get indiscernible sequences. So now we need to produce invariant types, and then that will give us a method for finding indiscernible sequences. So we've translated the problem. Now, one thing I should ask is, does everyone know like what an ultrafilter is and have experience with working with them? Like, I guess this is a thing that's done in the first model theory class. Okay, so we won't actually talk about ultra products, but we're going to use ultrafilters in a sort of different way, and in a way that's kind of. I always thought this construction was very intriguing. So here's a construction. So suppose A is a set of tuples of the same length. Say inside the monster model. So small set. So small always means less than the size of the saturation. That's the important thing. And script D is an ultrafilter on A. Then for any set of parameters B, we define the average type of D over B to be what? It's the set of formulas phi x in L of B. So these are formulas that can involve parameters in B, such that if I look at the set of A in A such that phi of A is true, that's big with respect to the ultrafilter. So one intuition that you might have is you think about D as like a measure on the elements from A. So let's say I've got some set A, and then I've got a set of parameters B, and given any formula, so if I'm given, say, like phi of x will define some set like this. And I look at the intersection of the set defined by phi of x with A, and I ask, is this big or not? Is this in D? And if D says it's big, then I put it in the type. And if D says it's small, then I don't. But because it's an ultrafilter, I make a decision about every set or its complement. And so this will, as it turns out, determine a complete type over B. Okay, so this is just some construction. It's a set of formulas. There's no reason to believe that it should have any particular properties, but it turns out to be a complete type. So let's prove that. So let's make our observations. So I'll leave the picture up. So observation 1 is that the average type of D with respect to B is a complete type over B. And 2, that av D over B is B invariant. And somehow this, I think, is a bit clearer than what was happening before. So why is it B invariant? Well, the question of whether or not, oh, no, sorry, it's not B invariant, it's A invariant. It's A invariant. A is the set that D is on. So the question of whether or not a formula goes in or out of the type is really determined just by information in A, namely which sets in A are big. And that's going to be more or less the proof why it's A invariant. Okay, so let's prove these things. And this will be the last thing we do today. And then we'll finish the second proof of the lemma at the beginning of tomorrow. Or not tomorrow, Wednesday. Okay, so first thing, we want to prove that this is a complete type over B. So what is it that we need to prove? So first we need to prove it's a type, namely that it's consistent, that it's a consistent set of formulas. And secondly, we need to prove that it's complete, that every formula gets a decision. These are the two things. So this is really proving two things. So first question is, why is it a type? Why is it consistent at all? So if av D, sorry, I'm barely capable of writing. If av D B is not consistent, then by compactness, there are phi 0 x through phi in minus 1 x in LB such that it's not possible to realize them all at the same time. Right? So the set that they define is empty. Or sorry, I don't mean in LB, although they are in LB. I really meant in av D B. Sorry. So if a set of formulas is inconsistent, and there are finitely many formulas in that set whose conjunction is inconsistent, what does it mean for a finite set of formulas to be inconsistent? It means that there's no element in all of them, right? Okay, now the set of A in A such that phi I A is true, this is contained in D by the definition. each one of these formulas is in the set of formulas, avdb. So it had better be the case that, that the set it defines intersects A in a D large set. But ultrafilters have the property that they're closed under finite intersection. So the intersection of I less than n of A in A, such that I satisfy phi I A, is in D. But this is the same thing as the set of A in A that satisfy the conjunction. Which is empty by our assumption that it's inconsistent. So the empty set is in D, but that contradicts the definition of an ultrafilter. Part of the definition of an ultrafilter is that the empty set is not one of the sets that's considered large. Okay. So this says that at the very least, it's consistent because we did a proof by contradiction. If it's not consistent, then there are finitely many formulas which give you, which define the empty set, and then the empty set is in your ultrafilter and it can't be. Okay, so consistent. Great. Now we need to check that it's complete, and this one's even easier. So suppose phi x in LB is a formula, and phi x is not an element of avdb. So what does that mean? We found a formula that's not in there. Then it had better be the case that it intersects A in a set that's not considered large by D. So the set of A in A, such that phi A is true, is not in D. So its complement is in D. So what is the complement of this set? Well, this is exactly the A in A that satisfy not phi A. Since since for every subset of A, either that set or its complement is in D. Okay. So what did we show? So we showed that not phi x is in av db. So we took an arbitrary formula which was not in av db, and we proved that its negation had to be. And that means that every formula either is in or its negation is in. And what does that mean? That means that it's complete. Okay, so that's our first observation. So you just take an ultrafilter on any set, and you take any other set of parameters, and then you use the ultrafilter to vote on which formulas go in and which formulas go out. The sets that intersect A in a big set go in the type, the set that intersect in a small set go out of the type, and that will always give you a complete type, which is invariant over the set on which you've defined your ultrafilter. It's kind of cool construction. So now let's just make one additional observation, which is that it's A invariant. So this is av db is A invariant. Okay, let's just see why. So fix some formula, phi xy, which is in L of A, and suppose we're given B and C, which are in B, such that B and C have the same type over A. What is it that we have to show? We must show phi x b is in av db if and only if phi x c is in av db. Right? This is what it means to be A invariant. That the decision of whether or not the formula goes in or out of the type is determined not by the identity of the element, but rather its type over A. Okay, so this is simply a matter of unraveling the definition. So let's do it. So phi xb is in av db if and only if, okay, the set of A in A such that phi AB is true, is in D. But notice that because B and C have the same type over A, this happens if and only if A in A such that phi AC is in D. Why? Because these two sets are equal. If you had some A such that phi AB was true, but not phi AC was true, then that would be a formula in the type of B, which was not in the type of C. So it would distinguish them, but you've assumed that they're the same. And then this happens if and only if phi xc is in av db. Okay, so now what is our strategy going to be? So this is just for next time. We're given our monster model. We've got some set A, and we've got our given sequence I. And we want to find some type, or sorry, we want to find some indiscernible sequence, J, A indiscernible, which closely resembles A in the sense that it realizes the EM type. So what we'll do is we'll fix some arbitrary ultrafilter, D on I, and we'll use the ultrafilter to vote on the generic behavior of the sequence I, and we'll let J realize that. So then J will be a sequence. So J will be a sequence, let's say BI, I less than omega, such that BI realizes av dA over B less than I for all I. So we end up building J like this. Now, because this is because this is I guess we should include I here too. So then we will have a sort of check that this ultimately ends up being A indiscernible and mirrors the behavior of the sequence we care about. So we know it's going to be indiscernible because of the lemma above, and then using the properties of ultrafilter and sort of the definition will prove that it realizes the EM type as well. So that's going to be the task for next time, which we'll do from the beginning. And this will give us a totally different argument. Notice there was no Ramsey theory in sight. A totally different argument for the existence of indiscernibles with the properties that we want. Okay, so that is it. So I'm going to stop recording. And are there any questions?
I have